Hello boys and girls and everybody else. Welcome again to another science video lesson. And for today's video lesson, we will be on our last topic for our module number 2, that is the physical nature of light. Come join me as we unravel the mysteries of the dual nature of light here in our lesson. Alright, so here we are in our lesson for today. So, dual nature of light. So, before we go to the main thing about the dual nature of light, so let's connect this one to something that is more profound other than science. So, have you heard, alright, so have you heard before the idea of duality of man? Alright, so duality of man. So, what is that idea all about? So, this is the okay, before we go to the dual nature of light. So also humans have also its known for its duality. All right, known for its duality. So what is this dual nature of man? So the idea was, all right. So the idea was that man, all right. So man can capable or are capable of doing good and evil deeds. All right. So that's the dual nature of man. All right. So as you can see on this picture, there's a duality here that is happening. Alright, so there's a duality that is seen on this picture. So sometimes man can do good things and sometimes man can do evil deeds. Alright, so that's the duality of man. And it is similar to our topic for today. Alright, it's similar for our topic for today. It's because of one thing. It is same as duality of light. Alright, so duality of light. So what is this two nature of light? Alright, can they be both? Or can they be one entity? Or they can be another entity. All right. So let's try to discover that one. So we are on the same module, the physical nature of light. So we are in the same module, the physical nature of light. And we are done already with the forms of electromagnetic radiation. All right. So I have the link. Alright, so just click on the link above. Alright, so just click the link above to access that video if you want. Alright, so for today, we were going to talk about the dual nature of light. So what is this dual nature? Alright, so lately, there's a photograph that is circulating in the social media that there's a direct observation. This photo is the direct observation of the particle and wave duality of light simultaneously. All right, so this is a clear picture of how light behaves. All right, how light behaves and what is the nature of light that we are dealing with. So we have here the wave on top, and the one at the bottom is the particle form. All right, form of light that we have right here. All right, so if you are wondering how this picture is made possible. All right, there's one device called the ultra-fast electron microscopy. All right, imagine that light is super fast. Right, light is super fast, and there's this device that can be used to picture. All right, picture out how the nature of light behaves. All right, so hopefully, thankfully, rather. All right, so thankfully we have a device that we have right here that we can use to picture out the wave and particle form of your light. Okay, so that is the ultra-fast electron microscopy. All right. So, before we go to the main thing, okay, so there's one person named Isaac Newton who said that light is made up of particles. And there's one person, all right, who contradicts that idea that light is made up of, or light is a wave. All right, so that is Thomas Young. All right, so when Einstein came into scene, all right, when Einstein came into scene, he said that why not both? Okay, so why not both? All right, so that is why physicists, modern physicists, hail him as a hero. Okay, so that is how Einstein perceived what light is all about. Okay, so for today, we will going to discover what makes the light a particle and what makes the light a wave. All right, so okay, and we will consolidate them as two entities. All right, okay, as what Einstein said. So, can a particle be a wave? Okay, so as you can see on this picture, an electron was fired on the other end. And when an electron passes through these two slits that you have right here, these two holes that you have right here, these two opening, okay, as you can see, it creates a certain pattern. And this pattern, according to some extent, is a manifestation that this particle can be a wave. Right? So the pattern that you see here on this observation screen that you have right here indicates that this particle can be a wave. Alright, so how is this pattern possible? Because of one thing, we called it interference. Alright, so we called it interference. So what do you mean by interference? Interference is the combination of two or more waves. Alright, so this is the combination of two or more waves. It can either reinforce each other or it can either cancel each other. Alright, in terms like constructive or destructive interference. Alright, so now, can a particle be a wave? So, probably. Alright, in this picture, it can be. Okay, so now, I just want to show you the Young's double slit experiment, whereas a single ray of light that you have right here creates a lot of pattern because of this said interference. Alright, this said interference that we have. Once the light passes through the slits that you have right here, it creates this certain pattern. Alright, certain pattern that tells us that light is a wave. Alright, so there's one person who proposed that idea, who contradicts the idea of Isaac Newton that light is a particle. So according to Thomas Young, he wants to prove that light is a wave because all waves, alright, all waves behaves, alright, okay, all waves, they have the ability, or they behaves, they interfere with one another as part of their behavior, alright. As part of the behavior of waves, they likely to interfere each other. Alright, so in short, when we are talking about waves, waves are likely to interfere once they interact with another wave. Okay, so according to him, okay, if Isaac Newton is correct, alright, so if Isaac Newton is correct, okay, so if light is a particle, now once light passes through these slits, logically speaking, that you will see two patterns on the other side. Right? You will see two patterns on the other side. Okay? But Thomas Young disagree on that light is a wave. Light is subjected to interference as well, just like a normal wave. So what we have right here, once the light source passes through this slit that you have right here, it will not create only two patterns, but it will create several patterns that you see here. One that is brightest at the middle and dimmest on both sides. Okay. So how is this possible? All right. So according to Thomas Young, this is what he expect. If light is a wave, this is what he expect. So he did an experiment. This is the infamous Young's double slit experiment. Okay, so we'll go now to our simulation just to visualize how this Young's double slit experiment works. All right, let's start first with a wave. Okay, let's start first with a wave. Okay, as we all know that wave, so I have right here a PET simulation, so you can go to their website. I put the website down okay, in the description of the video below. You can visit their website, and there are a lot of simulations that you can have there, from physics, bio, chemistry, and earth science. You can use them, okay, and as visualization of what is happening in our physical world. All right, so let's have this simulation about waves. So as we all know, we will use this. We will not use the water wave here. Instead, since we are talking about light, we will use light instead. All right. So the light itself, okay, light is a wave according to Thomas Young. So it is a wave. So it causes some disturbances on your medium right here. Okay, as it travels through. Okay. So as you can see, as we change the color, so this wave patterns also changes. Okay, so that is a wave. Now, when the wave, okay, encounters another wave, when a wave encounters another wave, they form what they call interference. There are two kinds of interference. We have constructive and we have destructive interference. When we say about destructive, or when we talk about destructive interference, these two waves cancels each other's out. Right? It's either they have two different amplitudes, all right, or they either have two different wavelengths, all right. So they cancel each other's out. Next one, when we talk about constructive interference, these two waves have same wavelengths, all right. They have same wavelengths or even frequency, or even they have the same amplitude. So when they combine, all right, instead of canceling each other's out, they reinforce each other. All right, so they reinforce each other. So what happens to the wave? It's either it increases its intensity or something like that. All right, so I have right here a two light that we have, and we will turn it on. So let's see what happens. So as you can see on this part, let's pause this. On this part, the wave is starting to interact with the other wave. Alright, so the waves that we have right here are starting to interact with one another. They're starting to interact with one another, forming these patterns that you have right here. This is the pattern of interference. Right? This is a pattern of interference. Again, interference is possible if you have two or more waves. All right? If you have one wave, if you just have one wave, it is impossible. So, as we continue this one, the interference, all right? So the interference between these two waves, all right, are being transmitted to the other side of the screen. All right, so that is the interference. Now, my question is, all right, you can answer this one in the comment section below. All right, so you can pause the video and answer this one in the comment section below. Now, what is it possible? All right, is it possible to produce an interference with just one wave? All right, is it possible to produce an interference? So, logically speaking, it is impossible, but experimentally, that is possible. All right, so we go now to the experiment Young did on 1807 in proposition that the light is a wave. So let's go to that experiment. Now, if we use a barrier, something like this, right? So if we use this barrier, okay, we can produce an interference only just using one light generator that we have right here. All right. So as you can see, if you use one, okay, as you can see, if you use one, the thing here is, okay, so the thing here is, there is no interference that will be seen, all right, in the simulation. Okay, so as you can see, now, according to Thomas Young, if the wave pattern is like this in the observer screen, if the wave pattern is just like this in the observer screen, then therefore, wave or light is a particle. All right. Now, he wants to prove that the wave is, or the light is a wave. So, he used not only one slit, but he used two slits. All right. So, he used two slits, and here's what he got. Okay. So, here's what he got on this, on his experiment. All right. So, he allowed the light to pass these two slits that you have right here. Now, instead of having one common pattern, just like what we have a while ago, instead of having one common pattern, we have now three patterns that you have right here. And they are separated by black regions that you have over here. They are separated by black regions, these lights that you have. So according to Thomas Young, as he expect, okay, these patterns will be formed. Right? These patterns will be formed, and he concluded that light is certainly a wave because of this certain pattern that you have right here. Now, if you take a look at the intensity on this screen, Okay, so let's try to change color. Let's put it in yellow. Right, something like that. Okay. So as you can see, the light pattern that you have right here is the same all throughout. All right, whether it is a green, a yellow, a red, or a violet, or even a blue, okay, it will generate the same pattern. In which the higher intensity of light is at the middle and the dimmest part are on the sides. Okay, so if I'm going to ask you, all right, if I'm going to ask you, where's the constructive interference happen? All right, so you can pause this video if you want. Where's the constructive interference happen? Is it at the middle or at the sides of this pattern? All right. So the answer to that is at the middle. So as you can see, the intensity of light increases at the middle. So it means that they are reinforcing one another. The waves are reinforcing one another. So what happens there is at the middle, constructive interference can be seen and destructive interference can be seen on both sides. Because this dimmer part tells us that the waves are canceling each other's out. All right, they are canceling each other's out. So that is what happens on this side that we have right here. All right. So okay, so this is the experiment created by Thomas Young. Okay, in 1807, and this is infamously called the double slit experiment by Thomas Young. Okay, so that is the pattern that we have right here. So what he again, before we leave this simulation, what he concludes here is that the light is a wave. All right, so let's go back. All right, so because of that particular experiment, we have now an idea that light is a wave. So aside from being a wave, what is the behavior that we observe on that particular experiment? Number one is interference, and number two, all right, and number two is, okay, what are these behaviors? So what are some ways that light behaves like a wave? All right, so that's the question that we will go. If light is a wave, what are the ways that light behaves like a wave? Okay, a typical wave. All right, so okay, we will try to find out what is the exact purpose of this polarizer in the wave theory that we have right here. All right, so like sound and water waves, all right, like sound and water waves, light shows interference, like what we did earlier. Next one is diffraction. So what is this diffraction? And also polarization. Okay, so polarization. What is this diffraction and polarization as part of the behavior of waves? Okay, so as you can see here, alright, so as you can see here, if light is a particle, there just only be one pattern that you will see. Right? But light is a wave. It has the ability to pass through an opening. Alright? It can pass through an opening. Okay? Not much wider than its wavelength, and it performs this process called diffraction. Alright? So what is diffraction? It is the ability of the light to bend and pass through a certain opening. Okay, so to show that what is diffraction is all about, okay, now observing this pattern that you have right here means to say that your light performs diffraction. And diffraction is one of the behavior of waves. Alright? Diffraction is one of the behavior of waves. It includes the interference that we have a while ago. Alright, so in this case, where is the diffraction in this simulation? Right? Where is the diffraction in this simulation? The diffraction happens when the light enters the two slits that we have right here. Once the light enters the two slits that you have right here, it performs your diffraction process. Okay? So the light bends as it passes through the slits, and as it does, it interferes with another wave that is produced on the other slit. Alright? So that is why it forms this certain pattern that you have. Again, if you have seen this pattern, it tells you that the light interferes, and the second one, the light diffracts. Okay? The light interferes and light diffracts. Okay, so now, basic application of this one. All right, so what is the basic application of this one? All right, example, in sound. Right, in sound. Okay, we have some instance that we can hear two people speaking. All right, we can hear two people talking to each other, even we are situated on a corner. All right, on a certain hallway or room, something like that. So we can still hear people talking to each other, even though we are located in another corner. Right, in a corner. So how is this possible? Because sound can bend in corners. All right, they can bend in corners. Okay, so how about light? All right, what is the practical application of this one to light? Okay, so for example, we have here Wi-Fi signal. All right, suppose your router creates this Wi-Fi signal. How is it possible that you can still receive this Wi-Fi signal even though you are in a certain room and your doors are closed? Okay? How is it possible that you can still receive this Wi-Fi signal even though you are in a isolated room and your doors are closed? Okay? So that is one manifestation of diffraction. Another one. Okay, how is it possible that the radio waves can be transmitted even though there are mountains? All right, even though there are mountains in its obstacle, all right, in its path, all right, as an obstacle. All right, so that is one situation where you can see the manifestation of diffraction. Okay, so okay, so the formation of shadows. Okay, so if you want to try this one out, you go outside and put your hand. All right, so put your hand under the sunlight, and you can see that your shadows are not perfectly edged. All right, the edges of your shadows are not perfectly possible. It's because it has something like fuzzy ripples on the sides. All right, you can see. Okay, you will see on your shadow. You will see on your hand's shadow that there are edges. The edges are fuzzy, like the one that you have right here. Okay, there are fuzzy sides. Now, these fuzzy sides that you have is a manifestation that there is what they call diffraction. Okay, there's what they call diffraction. That the wave diffracts. Okay, so it tells us that light is a wave. All right. So the one that you have right here is made up of one circular cardboard. All right, with no hole at the middle. Okay, so how is it possible? So guys, how is it possible that you produce a center on a cardboard that doesn't have any hole at all? Yan. Right? So this one also has fuzzy edges. The shadow of this blade has fuzzy edges. Also with this one. Right. So you can do this simple experiment, guys. You can do this simple experiment by cutting a cardboard. Right? By cutting a cardboard, do not put hole in at the middle and put it under a bright light. All right? So put it under a bright light and you will see that there will be a hole at the middle even though you didn't even though you didn't poke a hole on the middle of your cardboard. All right? So you can leave your answers in the comment section. How is that being possible? All right. So, what is diffraction? What is this diffraction? So let's take a look at again in the simulation. Okay, so what is this diffraction? So as you can see here, all right. So as you can see here in this diffraction, that the light, all right, that the light that you have right here, okay, this one is capable of entering or capable of passing through this hole. It creates these patterns that you have right here. Okay, so it creates this pattern. So as you change this color, so depending on the wavelength, the patterns also changes. Right? So the pattern also changes depending on wavelength. Okay? So As you can see, if you change the okay, if you change the pattern that we have right here, so it will follow the shape of that particular pattern, right? So more so with this one, okay? So and another one, the one that you have right here. So as you can see here, the light tends to go inside this opening. Okay, then tends to pass and bends on that opening. Now, this ripple effects that you have right here, is the sign that your light is interfering with one another. Okay, the light performs this what they call interference. Okay, so let's go back now. So that is diffraction. All right. So, what are the practical application of diffraction? Okay, so we have now interference and diffraction. Now, practical application of diffraction is the diffraction grating. All right, you can put these parallel slits on a glass or a plastic. Okay, like the one that you see here, the CD-ROM that you have right here, or the DVD-ROM that you have right here. It contains these grooves. Alright? It contains these many slits that you have on this CD-ROM. And the patterns that you see here, it's because of the slits or grooves that are etched in this plastic. Okay? In this CD-ROM that you have right here. So, it acts like a parallel slits that you have, and you have so many of them in this CD-ROM. And once the light passes through those slits, it creates this pattern. So we called it diffraction gratings. Alright? So we called it diffraction grating. So, okay, when light goes through, it diffracts, okay, in this diffraction grating. So again, it has the same pattern, just like what Thomas Young saw, okay, centuries ago. So we have this central bright spot, and we have this dimmer sides that you have on your patterns. Okay. Now, what is the upgrade? All right. So what is the practical application of diffraction grating? That is the spectrometers. Okay? Spectrometers are special kind of prism. Alright? These are special kind of prism that performs what they call diffraction. Right? It performs your diffraction, and this creates a spectrum of colors. Right? So you know already the spectrum of colors. Like in the visible light, we have Roy G. Biv. Alright, for example. So, the light source will pass through these openings that you have right here. Instead of creating one color, in a spectrometer, it will create a lot of colors. Right? From Roy G. Biv. Right? Starting from red down to violet. Alright, in just one light source. Okay. And just like diffraction grating, right? Just like diffraction grating, it has so many parallel slits. That creates this so many patterns on the other side. Okay, and when it creates pattern, you can see now the visible spectrum that a certain light source emit. Okay, this is the visible spectrum created from hydrogen. Okay, so how does it work? Okay, so this is a standard science experiment. So you have your Bunsen burner, right? So you have your Bunsen burner, and you put some unknown element on it. All right. For example, you put some unknown element on it, and then the light that it will produce will pass through a single slit, making it concentrated on this side. And once it passes through the prism, all right, it will create these colors. All right, so it will create this bright spectrum that you have on the other side. Now, the bright spectrum on the other side is the signature color of that unknown substance. Right? So that is the signature color. So whatever color patterns that you see here on the other side, that's because of your diffraction. Right? That is because of your diffraction. So, more so, okay, so how is this possible? Now, that is possible because an atom performs what they call absorption, and emission. Okay, absorption and emission. So what does it mean? So if the atom, so as you can see here, right? So as you can see here, if the atom absorbs an energy from ground state, which is this is the ground state, all right? So from ground state, it becomes excited. So it jumps to the next energy level when it absorbs light. Okay, when it absorbs energy. Now, when it does, okay, it jumps from lower energy level to higher energy level. Now, when the time comes that the atom will go back to its lower energy level, like the one that you have right here, it emits light. That is what they call emission. Right? It emits certain wavelength of light depending on how far, all right, depending on how high the energy level it jumps up, right? So if there's another energy level here, if the electron jumps off, there is a certain wavelength of light that it will produce, right? So if it jumps up to the highest energy level, there's also a corresponding wavelength of light on that it will emit. Again, absorption, the electron will absorb energy, right? And jumps up from lower energy level to higher energy level. Next one, it will emit. Okay, it will emit light if it goes back to its lower energy level. All right, so that is your absorption and emission. So this is how it looks like. Typically, if you have a prism, this is what it looks like, the continuous spectrum. This is what it looks like. Okay, now, when an electron absorbs, all right, when an electron absorbs to a certain light source, it looks like this. Alright, so if you question what are those dark bands that you have right here? What are those dark bands? Those dark bands are the wavelengths of light that they will emit. As you can see, the dark bands are the one that you have right here on the emission spectrum are the bands that are missing. Alright, these are the bands that are missing. Okay, on the other side. Okay, on the absorption spectrum. So meaning to say that all the lights or all the colors that you will see here, all right, all the colors that you will see here are being absorbed by your electrons, and all the colors that you will see here are being emitted by your electrons in the process. Okay, so this is the absorption spectrum and this is the emission spectrum. Excuse me for that. Okay, so now what's the use of the spectrometer? The use of the spectrometer is to map out, all right, unique spectral lines of the elements. All right, so these are the unique spectral lines of the elements. And how does it work? All right, so as I've said earlier, that if you have one source of light, and if you put it, if that light source, all right, if the light from that source travels through a prism, it will produce a continuous spectrum. Okay, it will produce a continuous spectrum. But if the light source encounters a certain gas or encounters a certain light at the middle or certain material at the middle before it enters the prism, all right? So, meaning to say that this gas absorbs this color of light. Right? Absorbs only this color of light. Now, also, this gas can also emit once it passes through the prism that the light that comes from this cooler gas that you have right here. Once it passes through the prism, it can also emit light on this certain wavelength that you have over here. Right? As you can see, these certain wavelength are missing on the absorption line of spectrum. Right? So, the black bands that you see here are this one. Okay. So, these lines that you have right here are the one that is being emitted once the electron goes back to its lower energy level. Right? Okay, so these are the fingerprints of your elements. So how does it work? All right. So how does it work? Suppose that we have a violet light. Okay. Suppose we have a violet light over here, and it interacts with an electron. The violet light. All right. So this is the pattern. The signature emission pattern. If the violet light has the right amount of energy, all right amount of energy and frequency, right, on that electron, from lower energy level, it will jump up to the higher energy level, right? It will jump up to the higher energy level. So that is, okay, what it does is absorption. All right, so what it does is absorption. Now, once the energy is being expended, or once the electron is going back to the lower energy state, once it goes back to this position again, it will emit light. So guess what? What kind of light, or what color of light it will emit? The same color that it is absorbed. Alright? So that is violet. Right. Next one. What if the light encounters red? Okay, what if the light encounters red? Or the electron encounters red light? Like the one that we have over here. Okay? So what will happen? So we have here on the emission spectrum that it can absorb red light. Right? It can absorb red light. So it will absorb red light. Then it will jump up from this energy level. It will jump up to this energy level. Alright, so now when it is done, alright, when it wants to go back to the lower energy level, when it goes back to the lower energy level, it will emit a certain light. Guess what? What is the light? Red. Alright, so this is the emitted light. So the red one. So more so, if you have alright, so if you have a blue color, for example, like the one that I have right here. So if you have a blue color, okay, so blue. So if you have a blue color, so it will jump up to the next energy level. Okay, so it will jump up to the higher energy level. And guess what? Okay, for example, it jumps up right here. Okay, so it jumps up right here. Then it will emit a light similar to the color that it is absorbed. Okay, so for example, how about it encounters a green light? Alright, the green light doesn't have enough energy to make the electron excited. Right? It doesn't have enough energy to make the electron excited, so what will happen? So what will happen here? It will just absorb the green light. Alright, so the same thing it will do, the electrons also will also absorb yellow light. Alright, so the electrons will also absorb yellow light because in your emission spectrum, it doesn't have any signature of yellow. Right? It doesn't have any signature of yellow. So that is the mechanics over here. Okay? That's how you read the emission spectrum. Okay? That's how the electron use the emission spectrum that you have on this pattern. Okay. So we will use a simulation on that just to point it out to you. Okay, so in this simulation, we will going to use the, yeah. Okay, so the neon lights and other discharge. Again, this is from PET simulation. You can see this simulation on their website. So I will just put the link below this, the description of this video. All right. So as you can see here, we'll use hydrogen. Okay. Now instead of one atom, we will use multiple atom, and let's put a spectrometer at the bottom. Right. So, we will fire a continuous flow of electrons. Alright, so we will fire a continuous flow of electrons that you have right here, so that your hydrogen atom will absorb a lot of energy. So as you can see here, this is the spectral signature of hydrogen. It has UV light. Right? It has ultraviolet. It has blue. All right, so rather violet. Okay, so we have cyan, we have red, and also it emits some form of infrared light. Okay, This is for the hydrogen. Now, what if we change the element? Instead of hydrogen, we have sodium. So, do you think they will have the same spectral lines? Do you think we can produce the same spectral lines? All right. So, write it down in the comment section of this video. So, let's see. All right. So, in sodium, okay, so there are no UV light that is produced. There are no UV light that is produced. The only produced is some wavelengths of basically 400 or 320. All right, and we have your yellow and then orange, which is if you burn a sodium. All right, when you burn a sodium metal, it will produce yellow and orange color. Right. So it produces infrared colors, that the one that you have right here. The one that you have right here. So basically, this is the spectral color of sodium. Okay, let's use another element like neon. Alright, so this is the spectral signature of neon. So as you can see, it is completely different from hydrogen. It is completely different from sodium that we have a while ago. So it will produce ultraviolet light, right? It will produce ultraviolet light. It will produce green light, and we have your yellow, orange, and some red, and very few amounts of infrared. Right? So that is the neon lights. Now, what is the practical application of this thing that I'm showing you? What is the practical application of this thing? Practical application is if you happen to see a neon lights, in signages, those are the practical uses of this concept that we are having right now. That is the practical application. All right. So aside from that, okay, we can also use this application to map out all the spectral signature of elements. So as you can see, all right, so if we will zoom that one in, as you can see, there are no elements that has the same spectral signature. Meaning to say, each of the spectral signature that you see here are unique to one element and that element alone. All right, so you will not see duplicates of that spectral signature, right? So even the heavier elements that you have at the bottom. Okay? Right. So that is the spectral signature of the periodic table of elements. Next one. Also if you fit a spectrometer, all right? If you fit a spectrometer on your telescope, you can see what are the stars are cooking. All right? What elements the stars are cooking inside their huge bulk. All right? So what is cooking inside the stars? Okay, what elements are they cooking? For example, we have here a star named Castor, we have Pollux, we have Betelgeuse, and we have Capella. So, if you study this absorption spectrum that you have right here, you will see those dark bands. And if you analyze those dark bands, you will see what kind of element they are cooking. Alright? What kind of element the stars are cooking. Okay, so with the use of the spectrometer. Alright? So, as you can see here, right? Okay, so this is an example of the absorption spectrum of the sun. Okay, now if you study it carefully, you will see that the sun itself is cooking up iron in its core. Alright, it starts to cook an iron in its core because there are spectral lines of iron that can be seen on the absorption spectrum of the sun. Right? There are unique lines. These lines that you have right here are the unique lines of iron. So you will see it on the absorption spectrum of the sun, and we can conclude that the sun is already making up an iron inside its core. Right? So amazing, right? So by just looking at the sun, by just looking at a certain star, you will see what element are they are the star are these stars are cooking inside their core. All right. So the next one. So we have now diffraction. We have now interference. Then the third one, we have polarization. Right. Now, the orientation of light is called polarization. Alright, so what are these orientation of light? Alright, only transverse wave has this certain orientation. Alright, only transverse wave. Longitudinal wave doesn't have this. Alright, so what are these orientation? So, the light moves vertically. Alright, so if you shake this string vertically, then therefore, the orientation of that light is vertical. So therefore, we can call it vertical polarization. Alright, next one. If you wiggle, alright, if you shake this string sideways, then therefore, the orientation of that wave is horizontal. Okay, the orientation of that wave is horizontal. So therefore, its polarization is horizontal. More so, okay, so the light itself has two polarization, the vertical and the horizontal polarization. Not to mention, also it has diagonal polarization. Alright? It has also a diagonal polarization. So we will just focus on vertical and horizontal here. Actually, there are many orientations of light that you have right here. And only, remember that only transverse wave has this polarization. Alright. Alright, so what is a polarizer? This is the materials that allows light of a certain orientation pass through it. Right. So, the one that passes through that polarizer is called polarized light. Right? So, the one that passes through that polarization. For example, this is your polarizer. If your polarizer is designed to polarize vertical orientation of light, then therefore, it will filter those vertical orientation. What goes to the other side is the polarized light. Right? Polarized light. All are horizontal. Now, if you have horizontal polarizer, then therefore, the one that goes to the other side is a polarized light, free of horizontal orientation, right? Of your light that you have right here. So because unpolarized light has so many orientation, right? Polarized light has so many orientation, then the polarizer is used to filter out any orientation that you like. Alright? So, what it does is, if you have seen a polarized glass, alright, so if you have seen a polarized glass, what happens when the light enters a polarized glass? It decreases its intensity. Alright? It decreases its intensity by filtering out certain orientation of light that passes through it. Okay, so that is the polarized sunglasses. Alright. Polarized sunglasses are very expensive. Right? Because this material, the material that can polarize these glasses are hard to do. Okay? So very difficult to produce. Okay. Alright, and aside from that, LCD also, alright, LCD also uses this certain polarization. Alright, so LCD screens, LCD TVs, something like that, uses the idea of making use of polarized material to polarize light. Right. Alright, so the fourth one that we have right here, alright, now if light is a wave, it is prone to scattering. Right? If light is a wave, it is prone to scattering. Now, the question that we have right here, alright, so I know you are familiar with this question, why sky is blue? Okay, so why sky is blue? Right. Now, during what time the sky is blue? Right. Okay, during noon time. Alright, when the sun is high up in the sky. Right, the one that you see here. When the sun is high up on the sky, okay, when the sun is high up on the sky, okay, that's the time that the sky is perfectly blue, right? Why? It's because of one thing. Because the light itself, all right, the light itself passes through a small surface area of an atmosphere. Right? This is the surface area of the atmosphere that it passes through. All right? So this is the surface area that your light will pass through on a certain part of the atmosphere. So what happens here is, that most of the blue light, all right, most of the blue light on this position of the sun, all right, over here, most of the blue light enters to your eyes. That is why the sky looks blue during noontime, all right, or somehow late noon, all right, or before noon, all right, before noontime, all right. So that is why the sky is blue, because the okay, the light itself encounters small amount or surface area, okay, of your atmosphere in the process. Okay, so this question answers why the sun looks red when it is setting. Okay, so let's answer the question why the sun looks red when it is setting down. Okay, now when the sun is setting down, compared to the compared to its position at noontime, the position of the sun in the horizon is somehow the position of the sun compared to the horizon is lower, right? It's now lower. So what it does, okay, what it does is it encounters so much surface area on your atmosphere. All right? There's a lot of surface area on your atmosphere that it will encounter. So what happens is the blue light is scattered away from your eyes. All right? So the blue light is scattered away from your eyes, and the red light, right? The red light is perfectly aligned on your eyes when it sets. So that is why you perceive, right? You perceive that the sun looks red during sunset, right? So okay, again, the sun looks red because it encounters a thick slice of atmosphere, right? During that process, and the dominating color that passes through your eyes is red. The blue is scattered away from your eyes. Okay, in the process. Unlike the one that you have right here, the blue is scattered towards your eyes. Okay? So that is why the sky is blue. So we call this process as Rayleigh scattering. So, again, let's wrap this certain portion up. Okay, let's wrap this one, let's wrap this certain topic up. So we have here, light is a wave. So what is the behavior of waves? Okay, what are the behavior of waves that makes light a wave? Number one, light can undergo interference. Light can do diffraction. Light can do diffraction. The third one, light can be polarized. Alright? And finally, light can be scattered. So these are the four behaviors that makes your light a wave. Right? So with that, alright. So with that, that ends up this particular part of our topic that light is a wave. Alright? So okay, so we are now done with the idea that light is a wave. So right now, what we have here is the last part of our dual nature of light being a particle. So the key question that we have right here is, how does light fit into being a particle? Okay, so what are the things that we should take note of? Actually, we encountered this one before in the discussion of the properties of light. So if you will remember on that video, this particular equation that you have right here, which is energy is equal to Planck's constant times the frequency. So it tells us that a certain frequency, at a certain frequency of electromagnetic wave, it can have a certain amount of energy within that frequency. Okay, so we have this idea that the higher the frequency, the higher the energy the wave contain. So this particular formula that you have last time, this particular formula tells us that light is a particle. Alright? It tells you that light is a particle. So aside from that, Max Planck also described that the temperature, all right? The temperature is that the color of the light is dependent on the temperature. So the higher the temperature, the variation of the color of light will vary. For example, all right. For example, if the temperature is low, you will see no light at all, right? So you will see no light. But if the temperature is somehow increase, right? It's somehow increase, a material glows red, right? So the one that you have right here. But if the temperature increase further, right? But if the temperature increase further, according to Max Planck, the white color will be produced. Okay, as a result of that higher temperature that you have right there. Now, the white light that you have right here is a mixture of different range of photons. Okay? Different photons or different with different range of energy. Alright, so that is white light. It contains all the colors: red, orange, yellow, green, blue, indigo, and violet. Alright? Each of these colors that you have right there has a different range of energy that is produced in white light. Now, remember that photons was described by Albert Einstein on our previous lesson. Right? On our previous video lesson. He said that photons are packets of light. Alright? So these are packets of energy rather. Not packets of light, packets of energy according to Albert Einstein. So he said in the idea of photoelectric effect. Okay? So the intensity of light, according to him, the intensity of light is dependent on the amount of photons, all right, that you have on your certain electromagnetic wave, all right, or certain spectrum. Again, according to Albert Einstein's idea that the intensity is somehow dependent on the amount of photons that you have. Okay? So, again, photons are packets of energy. So, what do we have here on that what do we have on that idea? Okay, according to him, that the intensity of light is the combination of the number of photons and the energy per photon. Okay, so what we have right here, for example, we have here the red photons that you have right here. Okay, and we have here the blue photons that you have at the bottom. Okay, also, to make red light with an intensity of 1 Weber per square meter, it takes a lot of photon than it does to make the same intensity with blue light. Now, to give you a perspective of what is this idea all about, let's take a look at the simulation about photoelectric effect. Alright, so this is the simulation about the photoelectric effect as what Albert Einstein said. Okay, so the intensity is dependent on the number of photons. Okay, so now how dependent it is. Okay, let's start first with red. And on this simulation, again, this is from PET Simulation. You can visit their website to download this simulation and learn from it. All right, you can play and learn on this simulation. All right, so on the options, there is show photon. All right. Okay, so as you can see here, the intensity is 0. So, meaning to say the photon is few. Okay, something like that. So, if you increase the intensity, you increase the number of photons. But the wavelength that we have right now is very large. Alright, you have a large wavelength over here. So, it means that it carries small amount of energy. So, even though the photons, all right, even though the photons are on a red color light, has is so many, even though it is so many, it contains small amount of energy. All right, these photons that you have right here, it contains small amount of energy. Okay, so again, the intensity, as you decrease the intensity of light, the photons decreases. As you increase the intensity, the photons increases. Alright? So, the idea is, the amount of photon or the amount of photon doesn't tell you that the amount of energy is also greater. The amount of photon is inversely proportional to the energy it carries. Okay? So, the amount of photon is inversely proportional to the amount of energy it carries. Because, even though you have so many of photons here, the energy it carries is small. Okay, let's switch to violet. Okay, let's switch to violet. Now, if you compare, right? So if you compare red and violet that we have a while ago, if you will compare red and violet, violet is somehow has very few, okay, has a very few amount of photons. But the good thing here is, even though it has few amount of photons, it each photon contains a lot of energy. Okay? Remember that wavelength is inversely proportional to energy. Alright? So, we have few photons here. We have few photons here compared to your red light. Alright? We have few photons, but these photons that you have right here contains a lot of energy. So, the amount of photons is inversely proportional to the amount of energy it carries. Alright? So, ultraviolet light has small amount of photons but carries a lot of energy, while red light has a lot of photons. It contains a lot of photons, but it carries less amount of energy. Alright. So that is what Einstein tells us, the amount of photons and the amount of energy relationship. Okay? Alright. So we on this picture that you have right here, it tells you that the amount of photons is inversely proportional to each to the amount of energy. So inversely proportional to the amount of energy it carries, the photons. Okay, so alright, so what is the practical application of this idea? So with this particular idea that we have right here, with this particular idea, it tells us that light is a particle. Light truly is a particle. And the photoelectric effect that you see a while ago, this one. Okay, so the photoelectric effect that you have right here. So let's increase the let's change the wavelength. Okay, so the ability to produce electrons, all right? The ability to make electrons jump from this point to this point, okay, is the sign that the light is a particle. All right? It is a sign that light is a particle and it is made up of photons. Without these photons, this phenomenon is impossible. Okay? Without these photons, this phenomenon is impossible. The photoelectric is impossible. Okay? So, particle nature of light. Okay, practical application of this is the one, photoelectric effect, the one earlier. And also, we have some glow in the dark. Okay, so this is the the glow in the dark or photoluminescence. Okay, in the process. Okay, so what is the mechanism here? Okay, certain elements or certain materials absorbs light. All right, certain elements or certain materials absorbs light, and once they absorbs light, they gather this energy, right? They gather this energy in one place. Okay, now when for example, when this hand was removed, the area around that particular hand absorbs this light coming from this flashlight, and the shadow that you have right here, these are the area, okay, this is the area of the glow-in-the-dark plastic that doesn't receive any amount of light. So in short, it doesn't have energy. The one that has energy, that is stored light, right? Photoluminescence is the process of releasing stored light. So the stored light around this hand that you have right here, hand shadow that you have right here, is being released in the process. Okay? So, the brighter it glows, all right? The brighter it glows, the more energy it the more energy was stored in the process. All right? So, things like this one. Okay? Phosphorus is one good material. All right, it can do photoluminescence. All right, phosphorus. Okay, phosphorescent screen. All right, something like that. Okay, it's made up of phosphorus, and okay, this phosphorus or this material absorbs light. All right, absorbs light, and when you turn off this light, it gives off this light that they absorb in the process. Okay, so that is the glow in the dark. And another one, also, it is this particular effect or this particular idea about the particle nature of light. It is used in photocopying machine. Okay, it is used in photocopying machine and a lot of applications out there, right? So there are a lot of applications, solar panels, okay, solar power calculators, okay. So these are some familiar applications of your particle nature of light, okay. So is light a particle or a wave? They are both, okay. Light is both, okay. Can be a particle or can be a wave, respectively. Okay. So before we end up this video lesson, let's have a certain connection about this one in our daily application in daily life. Okay, we have here 3D. Okay, 3D movies. Okay, so as you can see, guys, when you enter a 3D cinema, you will notice that the movie was distorted. All right, unless you wear these 3D glasses. Okay, these 3D glasses are polarized. Some of them are polarized vertically. Some of them are polarized horizontally. And some of them are polarized in a circular manner. Okay? So, that is why when you change the position of your head while watching the movie and wearing the polarized or 3D glasses, all right, there's a certain position of your head that makes you that will make you see the movie in its perfect proportion, right? In its perfect proportion. But if you change the position of your head, something like this or something like that, if you change the position of your head, it will distort that image. Right? It will distort that image because the polarized, all right, the polarizer that are found on 3D glasses are designed only on one orientation. It's either horizontal, vertical, or circular. Okay, so it depends. So that's how 3D movies works. Okay, so without those 3D glasses, and without the idea of polarization, it is impossible to watch a 3D movie. Okay, so that is the practical application of your polarization. And with that, all right, so thank you everyone for staying a while and learning something for this video lesson. So I hope you did learn a lot of things about the dual nature of light. The light is a wave and light is also a particle. Okay, so if you learned something from this video, just hit the like button on the this video below. And if you want to be updated, all right, so the next video lesson that I will have next time is all about mirrors. Okay, so if you want to be updated on that video lesson, just hit the subscribe button of this video and hit the notification bell. Now, if you have a question about the topic that we have on this video, if you want to suggest something, all right, just write it down in the comment section below. It will help me a lot in the algorithm in YouTube, all right, if you do those things. All right, so that ends up our video lesson for today. So let's see each other. Stay safe, everyone, and
子供なのね夢を追って傷ついて嘘が下手なくせに